Okay, welcome back to this. Now we will see the junction of several lines, right. So, first you look into this diagram. Suppose there is one line whose surge impedance or characteristic impedance is ZC1, and line is bifurcated here, and the surge impedance of this line, this side is ZC2, this is also ZC2. These two are equal, we have considered for their present study. It may be different also, right, and this is the junction J is the junction. If you draw the equivalent circuit, here voltage is here coming 2 Vf, later we will see why it is 2 Vf, right, that is your forward wave, and this is ZC1 and current through this at the receiving side is I, this is the junction, and these two are in parallel, therefore it is ZC2, so current I. So, as both are equal, half I current flowing through this to ZC2 characteristic impedance, right. This one I will come later. Now, so and this figure 9c actually this is actually travelling wave, only voltage is shown, right, only voltage is shown. Now, figure 9c actually shows the travelling voltage wave being reflected and transmitted at the junction J, right. So, at the junction J, the impedance seen is that due to the two equal surge impedance Z2 in parallel, right. Therefore, equation developed in the previous sections are applicable as long as Z2 is replaced by half ZC2. Previously, we have seen that your for this circuit analysis, we have seen that line was terminated by only say one is ZC1, another was only ZC2, but in this case two parallel lines are there. Therefore, those ZC2 will be replaced by your half of replaced by half of ZC2, instead of ZC2 half of ZC2, rest will remain same, right. That is why the equation developed in the previous section are applicable as long as ZC2 is replaced by half ZC2. So, if we do so, then what will happen that your, for example, the transmitted or refracted voltage current can be expressed as in previous expression. Just now we have seen that V was 2 Vf and that was ZC1 plus ZC2 into ZC2. Now, that was for your line your what you call, one side is ZC1, another side was ZC2. Now, line is bifurcated parallel line. So, ZC1 is remains same, ZC earlier one thing was not there, only two junction, right, two overhead line maybe connection or one cable, one overhead connection, right, the junction. But now, this your what you call that line is bifurcated, this is that is why ZC2 in the previous expression just you replace Z instead of ZC2 you write ZC2 by 2. Therefore, V is equal to 2 Vf, the ZC1 plus ZC2 by 2 into, instead of ZC2 it will be ZC2 by 2. So, right, similarly, and current also will be 2 ZC1 divided by ZC1 plus ZC2 by 2 into IF. Therefore, your IF is equal to, where IF is equal to 2 Vf ZC1 plus ZC2 by 2. Previously, we have seen that when two lines are connected with different characteristic impedance or overhead line or cable and overhead line, whatever may be, we have seen IF was previously it was 2 Vf upon ZC1 plus ZC2, right. Now, this ZC2 is replaced by ZC2 by 2. So, that is why in this diagram it is 2 Vf, right, IF is equal to 2 Vf divided by ZC1 plus ZC2 by 2, because these two are in parallel. That is why IF is equal to 2 Vf upon ZC1 plus ZC2, but this in terms of ZC1 and ZC2 for overhead line, two overhead line connection or different characteristic impedance or one overhead line another cable connection, that these things are derived. So, in this case also, that this is your what you call that forward wave, that is voltage wave, and this is the junction while line is bifurcated, this side is receiving end. So, before arrival at the junction voltage was Vf, right. Now, at the your what you call at the junction, while the wave arrive at the junction, some will be reflected, some will be transmitted, right. So, in that case, when your voltage is reflected back, so it is your Vb, that is your minus Vb. So, here, so your direction is from reflected one from right to left, this side is minus Vf. So, naturally that magnitude, actually effective magnitude will go down. So, this is your what you call this is your junction point, and then V is that your receiving end side voltage V. So, this is drawn like this, but this voltage your transmitted voltage magnitude, right, that V, that 2 will be cancelled, actually it will be Vf into Zc2 divided by Zc1 plus Zc2, right. So, this way this is shown, one is this along this line, another is along this line, as both are equal, both have equal characteristic impedance Zc2 by 2 Zc2 and Zc2. Therefore, this is also V, this is also V, and this is the reflected wave, that is your Vb. That is why figure 9, that is C is the travelling voltage wave reflected and transmitted at junction of 3 lines, because this is incoming line, this is incoming line, and these two are outgoing line. So, that is why this is after arrival at junction, because this Vb is the Vf plus Vb is equal to V. So, it is actually this is the reflected wave. So, that is why that, and your if you want that what will be reflected wave, something I have made it for you for this one, Vf plus Vb is equal to V, that means Vb is equal to V minus Vf, right. So, your V is equal to this one, V is equal to 2 Vf upon Zc1 plus Zc2 by 2 into Zc2 by 2. So, 2 will be cancelled, these 2 will be cancelled. So, basically it will be V will be Vf into Zc2 divided by Zc1 plus Zc2, right, minus Vf. If you simplify this one, you will get Vb is equal to minus Vf Zc1 minus Zc2 by 2 divided by Zc1 plus Zc2 by 2. Same as before, only thing is that Zc2 is replaced by Zc2 by 2 and one minus sign, because reflected wave, right. So, negative sign. So, that is why if you look in this graph, that this figure B, see that this is that minus Vb. So, because of this minus sign, right, and this is your V, that is your transmitted or refracted wave, right. So, this is after arrival at the your what you call at the junction, right. So, next is, just hold on, next one is your termination through capacitor, right. So, whenever suppose you have a line, that is assume that you have a line, right. So, this line is terminated at capacitor C. So, same as before, voltage will be 2 Vb, this is Zc, the characteristic impedance line, and this is your capacitor C, right. Now, before proceeding further, I mean I will come to that, when the wave will reach at the end of this your what you call at the time at the capacitor end, at that time you know that when it reaches, capacitor will behave as a short circuit, right, and when it will reach the steady state, it will act as open circuit. So, same philosophy will be applied. So, now this is the wave travelling before arrival at the junction, this is the voltage wave travelling along this direction, right. So, from equation your 60, from equation 60, we know the refraction coefficient can be expressed as this, we have seen that tau is equal to your 2z upon z plus zc. So, this is equation 95, right, or in if you take the Laplace transform, then tau should be, because it is your it is capacitor, right. See, therefore, it will be your what you call 2 upon in z, you use 1 upon Sc, S is the Laplace transform operator, right. So, 2 upon Cs divided by Zc plus 1 upon Cs, because we are trying to represent in Laplace transform. So, because it is a capacitor, you know that it is a capacitor. So, Zc will be 1 upon Sc, right, and S is the Laplace transform operator. Therefore, the your refracted voltage we know this equation, V is equal to tau into Vf, this we know, and tau is this much. Therefore, Vs is equal to 2 upon Cs divided by Zc plus 1 upon Cs, and it is a step disturbance actually. That is why Vf is replaced the Vf upon S, because of the step function, because all the things whatever we are observing, there is a step function we have assumed, right. Therefore, if you simplify this one, if you simplify this equation, you will get that Vs is equal to 2 Vf upon S into 1 upon Zc Cs plus 1, right. So, or Vs is equal to 2 Vf upon S, you rewrite this equation like this, 1 upon Zc into C divided by S plus 1 upon Zc into C, and if you go for your partial fraction, then it will be Vs is equal to 2 Vf 1 upon S minus 1 upon S plus 1 upon Zc into C. This I am not showing, I think you know, right, you know that. You can make it A upon S plus your B upon I mean the way, if it is the way it is given, suppose 1 upon S into S plus A, you can write A upon S plus B upon S plus A. After that you can compute A and B, right. So, so that if you take the inverse Laplace transform, so Vt will be 2 Vf into 1 minus e to the power minus t divided by Zc into C. But this is not the your what you call not a travelling wave, rather it is the voltage that will be impressed across the capacitor. That means, this Vt is the voltage that will be impressed across the capacitor. So, it is not a travelling wave. So, we can tell like this, that there is a voltage that will be impressed across the capacitor. Now, if this is the Vt, then you have to find out current flowing through the capacitor. So, current flowing to the capacitor is that It is equal to C into dVt by dt, that is C ddt, and Vt just now we have seen this one. So, you take the derivative of this. So, you will get that It is equal to 2 Vf upon Zc into e to the power minus t upon Zc into C. This is equation 99, right. Therefore, and if you go for cross multiplication, this is required. So, your It into Zc, It Z into C is equal to your what you call that this is It into your Zc, this is Zc is the suffix here, right, because it is the characteristic impedance of the line, right. So, it is Zc, C is the suffix here. So, this 2 Vf upon Zc e to the power minus t upon Zc into C, that means Zc into It. So, Zc into It is equal to 2 Vf e to the power minus t upon Zc into C. That means, from equation 44 the reflected voltage can be expressed as this we have seen in equation 44, not showing again and again, because this we have seen. So, directly we are writing that your Vbt is equal to half, that is from equation 44, right, that is your Vt minus It into Zc. Now, is equal to half, that Vt is equal to your just now we have seen that Vt is equal to your Vt is equal to this 2 Vf into 1 minus e to the power minus t upon Zc into C. So, this one you substitute here, Vt is equal to this one, and then It into Zc, this one actually minus 2 Vf e to the power minus t divided by Zc into C. That means, your Vbt upper simplification, Vbt is equal to Vf 1 minus 2 e to the power minus t Zc into C. This is equation 100, right. Therefore, if you look into this, I mean suppose although here it is it cannot be your what you call your interpret that for example, for t is equal to any value, say any value, if we can interpret that. Suppose for example, suppose t is equal to 0, suppose t is equal to 0. Therefore, what will happen? T is equal to 0 means it will be 1 minus 2. So, so Vbt is equal to minus your Vf. So, in this case what will happen, that just little bit of understanding. So, in this case what will happen, that this is that, so this position of the voltage wave at various instant, two instants are there, this is voltage, this is voltage, just look at the one, the first one only more than enough, look at this one, right. So, put the capacitor, like I mean if you logically if you try to put the capacitor acts as short circuit at the instant of arrival of the forward wave. That means, when it will arrive, that while we are discussing about so your travelling wave, that so many shunt capacitors are there, inductor immediately your capacitor instantly it will be short circuited, inductor will be open circuited. So, it takes time to reach to the receiving end, but as soon as when it will reach to the receiving end, say, so capacitor will behave like a short circuit. So, if capacitor act at the instant of arrival of the forward wave, so at this moment the reflected voltage wave is negative, because the terminal voltage is momentarily 0. That means, your when your travelling wave is arriving here, travelling wave, that capacitor is short circuited, that means your this thing, suppose we know that V is equal to V A plus V B, but when travelling wave is arriving here, the capacitor behaves as a short circuit. So, momentarily this voltage will be 0. If it is 0, means that is 0 is equal to V A plus V B, that means V B is equal to minus V F at that moment, right. But after that capacitor will be slowly your charge, and when it will reach to the steady state, that this will behave as an open circuit. So, in that case what will happen, that your just hold on, and so the terminal voltage is momentarily 0, and the current of the forward wave, right, is momentarily doubled. So, I mean this one you can of your own you can verify that your what you call that current is equal to, actually current is equal to your I is equal to your I F plus I B, right. That I B is equal to V F upon your say Z C, and I B is equal to minus V B upon your Z C, right. But question is that V B is equal to minus V F, therefore, V F upon Z C and minus V F upon Z C. So, it will be 2 V F upon Z C, right. Therefore, it is V F upon Z C, I F is equal to forward wave current, I F is equal to V F upon Z C, but at that moment it will be 2 into V F upon Z C, right. So, momentarily, that is why we are writing here that momentarily the voltage is 0, but at the current of the forward wave is momentarily, that is your what you call that doubled. So, in that case your what you call that that means this is actually V F upon Z C, that means you can write 2 into I F, right, because V F upon Z C is equal to I F. So, that is your 2 I F. So, in that case, so as the capacitor become fully charged, then it behaves as an open circuit. So, when it is fully charged, now capacitor will act as a open circuit, that is known to us. So, in that, thus the terminal current becomes 0 and its voltage becomes equal to twice the forward voltage wave. So, in that case, if you look that is this one, right. So, if you look into that at any instant, when your what you call that V B is equal to minus V F, it is showing like this, and but after that capacitor will be slowly it will be getting charged. So, V should be is equal to V F plus V B. So, after that with that waveform, this one will be added, and this V will be your after arrival at the terminal, the termination, that V will move, V characteristic of the V will be like this. This is at a particular instant. Similarly, this voltage another instant also it will be the same philosophy, but one is sufficient for understanding, right. And the capacitor one, if you look at the capacitor one, that V is equal to this expression we have got it, V is equal to 2 V F 1 minus e to the power minus T upon Z C into C. So, when T is equal to 0, right, when T is equal to 0, V is equal to 0, and when it capacitor terminal voltage, that is after arriving this. So, finally, gradually it is increasing, and it is your what you call finally it is equal to the V is equal to 2 V F, right. So, that means that this is actually the capacitor terminal voltage, this whatever we have derived, right, and this is your your disposition of wave at various instant. So, this is that capacitor terminal voltage variation, and this one, either this one or this one, this is the your what you call, that is that V is equal to your V A plus V B, right, which is arriving at the your receiving end. So, this is for the capacitor. So, how we can decide either this one or this one, you can make it. Similarly, this is an exercise for you, instead of voltage you just plot the your what you call the current, right, because here all voltage waves are shown. So, I request you this one and this one, this is current waveform also, that is you should draw, right. So, this is your what you call the termination at capacitor. These are special cases, right, these are special cases, and in reality is something else. In reality it may not happen. And termination through inductor, it is just dual of capacitor. So, in this case capacitor, instead of capacitor C, you can replace this one by an inductor, So, it will just opposite, it behavior will be just opposite to the capacitor, right, and this is the characteristic impedance. So, in that case the circuit behaves like an open circuit line initially, right, and in the case of capacitor it was short circuit, in this case it is initially open circuit. So, a current cannot flow through the inductor instantaneously, this we know, but finally acts like a short circuited line. So, therefore, the inductive termination is the dual of the capacitive termination. It will be just what is happening for your current for the capacitor, it will happen for the voltage, I mean just dual, right. So, from the equivalent circuit the voltage across the inductor is. So, we can write this one, we can write your this thing, that V t is equal to V t is equal to 2 V f into e to the power minus Z c upon L t, this is your V t, and similarly the current expression of whatever we are getting for voltages, this terminology, that I t is equal to 2 V f upon Z c 1 minus e to the power minus Z c upon L into t. So, therefore, the reflected voltage wave is that V b t is equal to V t minus we know your V b plus V f is equal to V t, therefore, V b t is equal to V t minus V f t. So, this V t expression is known in terms of V f. If you substitute, then reflected wave, that V b t will get V f into 2 e to the power minus Z c upon L t minus 1, this is equation 104. So, this is actually your what you call, this is your inductor. If line is terminated, your what you call your in inductive only pure inductive your circuit, right. But in reality it does not happen, that only X should not be there, that resistance also will be there or in general Z, but this is a special case. For this one I will request you that you will draw the voltage wave, forward V f, then your V, and showing also the V b, right. This will be an exercise for you. Next is your, so up to this travelling wave more or less things are okay, right. I mean there is not much mathematics here, only little bit of understanding, and numericals also quite easy. So, which you can easily solve, right. Now, next one is that your Bewley lattice diagram, bounce diagram. I think it was given in 1951. So, nearly 66 years back, right. So, it actually gives some ideas, right. Suppose it will give it voltage at given point and time in a transmission system. So, it is a useful visual aid to keep track of travelling voltage or current wave as it reflects back and forth from the end of the line, because it will be sending and receiving end, it will be reflected back and forth. So, that question is that how to understand this Bewley's diagram, right. First thing is that before showing the diagram, that figure 11a. So, I will show that circuit diagram where Z s and Z r represent internal source impedance and impedance connected to the end of the line. So, Z s is the source impedance or internal impedance, and Z r is the your impedance connected at the end of the line, and figure 11b, t is the time for a wave to travel that line length. That means, it is shows, suppose you have this is the diagram, this is voltage, this across this V f, this is actually internal impedance Z s and it is small e f given, but across this the voltage is V f and this characteristic impedance is Z c, right, and receiving end side it is terminated Z r. Now, first if you look into this diagram, first you see how things are, lattice diagram is drawn. So, this side if you look, this side is time, t is equal to 0, capital T, capital 2 t, capital 3 t, 4 t and so on, this is time, and this side your distance, this is actually distance. Now, suppose at any instant we can find out what will be the voltage. So, what will happen, that this is V f, this is, that means what, this is at t is equal to 0 and this is at x is distance is x, it is t is equal to 0, x is equal to 0, and when it is travelling, that line length is x is equal to L, and your the two reflection coefficient, your rho s and rho r, both have been given. So, that is your what you call that expression we have derived earlier. Rho s is given z s minus z c upon z s plus z c, this is actually sending end side, and rho r is equal to z r minus z c, z r plus z c, this is at the receiving end side. These two coefficients are given. We have found out all your what you call that reflection, refraction, all these things we have made it, right. So, in this case what happened, that travelling wave travels. So, it is starting from here, right. When it is travelling, it is V f. Now, receiving side, the reflection factor is rho r. That means, this reflection will be multiplied by rho r. So, rho r into V f, right. And this printing is little bit small, but understandable. When you will see this one, this is understandable, right. Now, from the sending end, when again it will be reflected back, sending end side reflection coefficient is rho s. So, with this rho s will be multiplied. So, rho s rho r into V f, right, and this time this side when again when it will be reflected back, receiving end side, it will be it will be rho s, and this is actually a printing error, it will be rho s rho r square. It I am writing here rho s rho r square V f here, right. So, it will be, because it is reflecting from the receiving end side, the reflection coefficient is rho r. So, it will be rho s rho r square, not rho s square, rho s into rho r square into your V f, right, into V f. Now, when again it is reflecting from sending end side is rho s. So, it will be multiplied into rho s, that means it will be rho s square rho r square into V f, rho s rho r square V f is already there, and again it will be reflected. So, it will be rho s square rho r square V f. Now, again when it will come here, right, when it is coming here, again it will be reflected back from the receiving end. Therefore, this side again it will be multiplied by rho r. So, already it was rho s square rho r square. So, when it will multiply rho r, it will be rho s square rho r cube into V f, and when from this side and coming at 60, when it will be multiplied by rho s, it will be rho s cube rho r cube into V f, and so on, right. So, that way these things will be your what you call this lattice diagram can be constructed. So, this side is time, it is time t, it is given here, this is time. That means that the diagonal zigzag line represents the wave. Now, I have explained everything, but for you it is write up is here, that diagonal zigzag line represents the wave as it travels back and forth between the ends or discontinuities. Now, corresponding to the distance traveled, the reflections are your what you call determined by multiplying the incident waves by the appropriate reflection coefficient. This is sending end reflection factor or coefficient, and this is receiving end reflection factor or coefficient, right. So, the voltage at a given point in time and distance is found by adding all terms that are directly above that point. How to find out the voltage, I will come will be coming, will come back to soon. So, thank you.